Okay, we're going to continue on here. We're talking equilibrium, and obviously we continued our talk last time of Kc and Kp sort of calculations. Again, the formula that sort of ties those together: Kp equals Kc, RT delta N. R being our gas constant, same one you use in the ideal gas law, the 0.08206. And obviously that needs to be our temperature there in Kelvin. And our delta N, as we talked about, is the change in the moles of gas molecules. Remember, as we talked about a number of times, it's really important on that one that you do the products minus reactants again, because you could get a negative number, which obviously mathematically will allow you to or have you do something different than if it was a positive number. At the end, last time we talked about ways to sort of manipulate equilibrium equations, and sometimes you may have to do that if you're trying to figure out maybe equilibrium constant for a reaction from several other individual reactions. So remember that if you have an equilibrium reaction with a K value here, uh, if you needed to reverse that reaction, you would flip it around. And again, a reminder of what that does to the equilibrium constant is it actually means you take 1 over the equilibrium constant as your products become your reactants and your reactants become your products. We also talked about that you may need to maybe multiply an equation by a particular number, a common number. So if I needed 2a there, I can multiply the entire equation by 2. And that, when you do that in terms of the equilibrium constant, we actually take it and we would square it. So if you have to multiply a reaction by a common number, you basically take that common number as sort of the exponent there with the equilibrium constant, and that's how that changes it. Again, here you don't multiply the k value by the number. Again, you're going to take that as the exponent. Obviously, as well, if you needed to divide by a common number, so if I took this guy and divided him back by 2, that again would return me to our original equation. And what that would essentially do is we would take the square root of the k value in that particular case, uh, as we would be going from here to here, basically. And that's the same idea. So if you have to multiply, you take the k value to that number by a number. You have to divide by a number. You take the root of the k value to that number. And that again is the kind of manipulations of the equilibrium constant and the equations. Lastly, obviously, if you need to add 2 equations or more together, once again, what that does is we were to add these together, our C's would cancel, our D's would cancel, gives us A plus B goes to E plus F. When we do add the equations, we do not add the k values. We actually end up multiplying the k values. So you would multiply the k values together. Obviously, if you added up 3 reactions, you'd multiply all 3 k values together along the way. And as we did a couple of examples last time, again, this would be a situation maybe they give you several individual sort of reactions and you're trying to figure out a k value for another reaction. So you'd have some kind of manipulate, very similar to Hess's law, sort of kind of keep track of everything and what is k value. Any questions on any of that stuff from last time there? Okay. So as we were just seeing there, again, in typical units, molarity and atmospheres are the common units that's usually associated with any type of equilibrium calculation. So again, as we'll get into later calculations here, definitely if you're doing something with pressures, atmospheres, usually what you want everybody in when you're doing the calculation. And again, you may have to convert afterwards to some other unit, but molarity as well. And when we see an equilibrium constant value, again, as we talked about, there's no units associated with it, but it does give you some information about what's going on in that particular reaction. Again, as we talked about, if you have a large value of K, that means that mainly you should have products at equilibrium. If you have a smaller value of K, you're going to expect a little bit more reactants at equilibrium. remember that the only thing that affects the actual value of the equilibrium constant is temperature. So as we also talked about, again, if you did a multiple experiments and you kept the temperature constant, and in each experiment you use different amounts of reactants and products for every one, that ratio of products to reactants should come out to the same ratio as long as the temperature stays the same. And again, when we change it, say from 25 degrees to 40 degrees, comparison of the K values at those two temperatures will be different. Again, that is what we're talking about there. As we just saw there and talked about, for adding up equations, we're going to multiply them. Thank you. The K values together. And again, if you got to multiply a particular reaction, you're going to take it to that number. If you're going to divide, you're going to take the root of it. All right. And again, there's many different equilibrium positions. We'll always get a constant value of K. And when we do see K written for a reaction is specific for how that reaction or equation is written, what's on the reactant side, what's on the product side, and obviously at that particular temperature. All right, so we talked a lot about K, so let's just take a break for K for just a second here. Talk about a different letter in the alphabet, and that is Q. And Q is what's known as the reaction quotient. And Q is actually calculated the exact same way as you calculate K. So you would calculate Q exact same deal as you would do K. So you would take your products over your reactants. You would use the coefficients as the exponents, exactly the same calculation as you would calculate the equilibrium constant expression. So you may be saying, if it's the exact same calculation, what is Q for? So Q is really for two sort of things. There's sort of a straight up sort of Q type question, which is basically these two questions. The question is your system at equilibrium? So if you're able to calculate Q, you could answer the question of, is the system at equilibrium or not? And the second thing that you could answer from calculating Q is, if it is not at equilibrium, which way does it need to go to actually reach equilibrium? Does it need to make more products? Does it need to make more reactants to reach equilibrium? It will tell you that information. Now, because Q is calculated the exact same way as K, the only way you're able to ever calculate Q is if you have concentrations or pressures for everybody in the equation. So you would need information about everybody in the equation. And that's really why you would calculate Q, because you already have obviously concentrations of everybody in the reaction. So you don't know if you're at equilibrium, you're on your way to equilibrium. So that is really what sort of Q is for. So if you calculate Q and it's actually greater than the equilibrium constant, K value, your system is not at equilibrium. And in order to reach equilibrium, it actually needs to go to the left-hand side towards the reactant side. So if you put Q on the left and K on the right, it'll just go opposite of where that's pointing, basically. If you calculate Q and it actually does equal the equilibrium constant value, congratulations, you're at equilibrium. So you've reached equilibrium. If you calculate Q and it's less than the equilibrium constant, again, you're not at equilibrium. And in order to reach equilibrium, it needs to go make some products, basically, as opposed to reactants here, right? Those guys. So this is probably most often going to be used in just kind of a straight up question, like I just mentioned, is the system at equilibrium? Which way does it need to go to reach equilibrium? There is another place a little later on in the chapter here where we will see Q kind of pop back in, and that will help us decide sort of which way the reaction is going, or verify which way the reaction is going if we're not sure. So once again, you can only calculate it, obviously, if you have all the reactant information, all the product information given to you. If you are missing something, then you pretty much, in most cases, don't have to worry about Q or calculating Q, because there's no way for you to do that because you don't know anybody's concentration. So the idea here is, are the concentrations you're seeing, are pressures, are these like initial concentration or initial pressures, or are these like equilibrium pressures or concentrations? And that's really what Q is for. And once again, as I mentioned before, calculate the same as you would do K. Yeah. So again, exact same way. So why don't you try one here? If you if at the start of reaction we have 0.249 moles of N2 and 3.21 times 10 to minus 2 moles of H2 and 6.42 times 10 to minus 4 moles of NH3 in a 3.5 liter vessel. If the K value is 1.2, is the system at equilibrium? And if not, which way will it have to go actually to reach equilibrium? So take a few moments there, calculate up probably something like Q would be a good idea. We're doing so once again, we have some information about N2 here, H2, got the moles, and we also have the volume, and we also have some moles and volume of our NH3. So we do have information about everybody here in the reaction. So that probably is a very good indication in these type of problems that definitely Q is probably what you should probably calculate first. And definitely if the question asks this, and this is what I would consider sort of a straight up Q type question, is the system at equilibrium or not? So once again, to calculate Q, it is exactly the same way as we would write the equilibrium expression. So we would take the concentration of NH3, and just like we would do with K, we would square it because of the coefficient. We would divide it by our N2 and also our H2, which would need to be cubed, obviously, because of the coefficient as well. So it's basically the exact same way as you would write the equilibrium expression. Before we could go in there, we do need some concentration. So we got moles and liters. So we would probably want to calculate some concentrations here. So we have our N2, and that's going to be 0.249 moles over our 3.5 liters. We also have our H2, which is 3.21 times 10 to the minus 2 moles over 3.5 liters. And lastly, we got our NH3 here, which is 6.42 times 10 to the minus 4 moles over our 3.5 liters. So this is going to give us the concentrations of everybody, which is what we need to go into that expression. So we're going to go 0.249 divided by 3.5. Now we'll go 0.0711. 3.21 exponent -2, 3.5 dividing 0.00917, and lastly 6.42 to the minus 4 divided by 3.5, 0.000183 molar. So now that we have the concentrations of each of these, we could actually go into our expression here. And if we do that, looks like we got 0.000183. Once again, we do need to square it. Divided by our N2, 0.0711, and our 0.00917, that does need to be cubed in this case. And it looks like we will end up with, if I do a little squaring and dividing 0.0711, hit equals, divide by 0.00917. We're going to cube that thing. Yeah, it looks like we're going to end up with a Q value of 0.614 in this case. Yeah. First off, any questions on the calculation? All right, so what do we use that with? Well, we use that with the K value that was given to us here, and we can see that the K value is 1.2. So in this case, our Q is actually less than our K value. And because it's less than our equilibrium constant value, that first thing it tells us is we are not at equilibrium. Again, the only way they would be at equilibrium if they equaled each other, which they don't. And again, if you kind of write Q on the left and K on the right, it goes opposite the way this guy is pointing. So to reach equilibrium, you need to go in the opposite direction there and towards our product side in this case. Make more products. Any questions on Q? So as I mentioned, pretty much this is a straight up sort of Q question, and we'll see it pop up again a little bit later on. But obviously, as you can see, you do need everybody's concentration in order to be able to calculate it. So if you don't have that, then you pretty much don't have to worry too much about it. Any questions? All right, then let us get into, dare I say, the calculation of the season, what this class is all about, which is we're going to talk about solving equilibrium constants. problems. And to solve these, we're going to be looking for equilibrium concentrations. And also we can do this with pressures, and we could look for equilibrium pressures. So the way that we do this is really we use what is known as a ice table. And maybe you're familiar with ice tables or not. ICE stands for initial, change, and equilibrium. And it is really the calculation that we use the most in this class. And we see it come up in a lot of places. And like I said, maybe you learned it when you did limiting reagents in Chem 50. Probably not. Nobody teaches it anymore like that. They should, because then when you get here, you'll have seen it before, but they never do. They do these stupid do two calculations to the end and choose which one's the smallest, right? But maybe you've seen it. If not, we'll talk about what it is. But it really is what you want to use, and pretty much you should always sort of think of an ice table when you're doing an equilibrium problem. And I say that because after we go through all these chapters and stuff, I'm always amazed when people get to an exam and they never like use an ice table, and it's like in every question almost, right? So you almost can't go wrong with it. So how do we do this? Well, we say we have an equation such as we'll do A2 plus B2 goes to 2AB, very creative. K is equal to 10 or something. And let's say we were given some initial concentrations here of A, and we'll just say it was like 4 molar. And we'll say B was 2 molar or something like that. So the way that we would do this is you definitely want to always make sure you have the equation, and it does definitely need to be balanced. So like normal, if the equation is not balanced, it's going to really screw up your calculations. So like normal, equation needs to be balanced. You're going to go I here, which is initial, and we're going to put in our initial concentrations here. And in a lot of problems, you may not be given anything like how much products you have or anything like that. And if they really don't mention anything about products or anything on that side, it is usually fairly safe to assume you got nothing going on there, and you could start with zero basically on that side. Now, the change part of the table is kind of the important part, and it really is actually what you're going to be trying to solve for. And typically, we represent the change in a nice table with the letter X. So X is sort of our unknown, and that is typically what we're looking to solve for. Now, a couple of things you want to think about when you're doing this is which way this reaction is going to proceed. Now, in this particular example, in this situation, since I have no products, what is the only way this reaction can start? It has to go. It has to go in which direction? Towards the products, reactants, reverse direction, forward direction? Which way should it go? It's got to go really in the forward direction in this case, because you have no products to go the other way at this point, right? You only have reactants. They're going to come together. That's going to force really, again, the forward direction here of this reaction to take place. And that's important for the change part, because if the forward direction is happening, would I expect my reactants concentrations to be increasing or decreasing? Decreasing, right? Because the only way you can make products is to use reactants, right? And by the same token, I would also expect my products concentration to be increasing, right? Because we're going to start making some. And we represent in an ice table sort of decreasing and increasing with minuses and pluses. Minuses for things that are decreasing, pluses for things that are increasing. So this would be minus x, as it should be decreasing with time. This is minus x. And by the way, I am actually taking into account the stoichiometry in this equation. Cannot forget that. Each of these coefficients here are 1, and that is why it's minus x and minus x. When I get to the other side, which is our products, we would expect it to start to increase, but we also need to take into account the stoichiometry. And this is not a 1, this is actually a 2. And you do need to put it as 2x because of the coefficient. The change part, you do need to take into account the coefficients in the balance equation. That is what does the mole to mole relationship. Also, I could do like limiting reagents with an isostaple pretty quickly, super fast, because it does that mole to mole calculation for you without doing it individually. So you do want to, on the change, make sure that you do take the coefficients into account, because again, if you do not, you will have the wrong stoichiometry, the wrong mole to mole relationship, and obviously you will get the wrong answer in this case. When we get to equilibrium, we're basically just going to bring everybody down. And for the sake of making it a little clearer, I'm going to leave the molarity M off of it. And this is just going to be 4 minus X and 2 minus X. And this would be 2X. First off, any questions on the ice table? Now, what do we really want to do here? You see a lot of X's, so that's really what we want to do. We really want to figure out what is the value of X. And we could do that by using our equilibrium expression, because we could write that this is AB squared divided by 4 minus X and 2 minus X. Actually, I just combo that there. Sorry, let me just write that separately. Hang on a sec. Got ahead of myself there. We could write our expression like normal, which is AB squared, and this would be A2, and this would be B2, and that equals 10. And as you might imagine from what I just wrote, what we're going to do now is basically take our equilibrium line and put everybody into this expression. And when we take it and put it into this expression, we end up with 2x squared on top divided by 4 minus x and 2 minus x, and this is going to equal 10. At this point, it is fun math. Yeah, so you got to go solve some math problem right here at this point. Now, we do use things like the quadratic. Yes, a little quadratic, I know. That is something like ax squared plus bx plus c equals 0, where a, b, and c are used in x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. Yes. Hopefully that looks somewhat familiar. You've seen it at some point in your life. By the way, when I do use the quadratic, how many x values do I get? I do get 2x values, yeah. So you will get 2x values here. And one of the x values will not make sense. But how do we know what will happen? Obviously, here we would go and solve for x. And again, this is one way in which you could solve for x. There are other ways you can solve for x, but this is one way that you can do it. Once we do solve for x, the idea there is the x value that we get is all these x values in this table. And when you do get something like the quadratic, or if you use the quadratic, you'll get 2x values. And what will happen is with one of the x values, you'll put it back in and you'll get like a negative number, which obviously you can't have a negative concentration or anything like that. And that's the one obviously not to use, right? So you should use the other x value in that case. So in terms of math, this is going to be probably the most complicated math part of it. And like I said, there are some other ways that you can solve these without using the quadratic, and you don't necessarily have to always use the quadratic, but you can always use it if you like. But that is what we're looking for. So the idea here is we want to solve for x. Once we have solved for x, we then can put that x value back into that equilibrium line, and that then, like I said, should give you the equilibrium concentrations of everybody present. Any questions on that there? All right, so why don't we do one here, and we'll come take a look at it together and see what we're doing here. All right, so let's say we have this problem here where we have BR2 goes to 2BR. The equilibrium constant is 7. We have an initial concentration of BR2 as 0.663 molar. We want to know what everybody's equilibrium concentrations are at this point. So that is a big thing of equilibrium concentrations, equilibrium pressures. It should just ring a bell in your head. I should probably be doing like an ice table is pretty much the calculation I should be doing. So let's start with this. So the first thing that we could do is we can write our expression here, and our Kc is going to be the concentration of Br. Again, we're going to square it because of the coefficient. We're going to divide it by the concentration of Br2, and that's going to equal lucky number 7 here as it was given to us in the problem. So we will then go to our ice table here. And initially, obviously, this is the only concentration that was given to us, 0.663. And again, if there's nothing mentioned about the product side, pretty safe to just assume 0 to begin with. Once again, in this situation, because there is nothing really on the product side, we can safely also assume that this reaction should be heading towards the products, as obviously there's no products to go the other way, so it's got to be heading towards product. That again tells us that our minuses should be on the reactant side, and our positive guys there, our pluses should be on the product side. So the change here is going to be minus x, again for really the 1 for the coefficient there. This is going to increase, so it's going to be 2x once again for the 2 that is there as well. At this point, we are good to sort of complete our table, and we will end up with here just carrying everybody down 0.663 minus x and 2x. Any questions on the ice table here? All right. Now, as I mentioned before, our goal is to solve for the value of x so we can really figure out uh, what the change is, and that'll allow us to figure out our equilibrium concentration. So we're going to take everything we got, and we're going to basically stick it into our expression here. And if you do that, that is going to get you 2x that's going to be squared divided by 0.663 minus x is going to equal 7. So if we clean this up a little bit, the thing that most people forget to do is up on top ends up being 4x squared. People always like to square the letter, but not so much the number. So that's a very common error people make a lot. People go 2x squared and not square the number. So make sure you do that. We're going to go 0.663 minus x is equal to 7. We need to kind of get everybody to the same size. So we're going to multiply what's on the bottom to the other side. And if we do that, that will give us 4x squared is equal to 0.663 times 7. 4.641 minus 7 times x, which is 7x. Obviously, to get us into our quadratic, right, you're going to take everybody to one side of the equal sign. It honestly doesn't matter which way you go on that. Most people prefer to have the x squared being positive, but it doesn't really matter. You could have a negative if you want. I'm going to bring everybody over here to the other side, and that's going to give me 4x squared plus 7x minus 4.641 is equal to 0. And that is really my quadratic here. That is my A, right? My B and my C that goes in there. And a reminder that with the C, you do take the negative with it. Yeah. So the subtraction negative, make sure you take it with it. That is going to go into our x is equal to minus b plus or minus the square root b squared minus 4ac divided by 2a. Popping in some numbers here, we'll go minus b, which would be minus 7, plus or minus the square root. If you do everything inside the square root, which is 7 squared minus 4 times a, which is 4, times c, which is negative 4.641, you're going to end up inside the square root with 123.256, to which if you then take the square root of it, you end up with like 11.10. That's all going to be divided by 2 times A, which is 8. At this point, this is where we're going to get basically our 2x values, one doing the plus and coming back, and one answer doing the minus. So taking the plus root first, that's going to be minus 7 plus 11.10, basically, divided by 8, going to give us an x value of 0.513. That was the plus part of it. If you went through and did the minus, that's going to be minus 7 minus 11.10 divided by 8. Going to get you a negative 2.26 here on the subtract part of it. First off, any questions on that there? At this point, you could hopefully see that the one that probably will not make sense is the negative one, because obviously if I put my x back into the 2x, that's going to give me a negative concentration. So that is not going to be the correct one here. That would mean that this guy here should be our correct x value in this case. And if we do that, that means that the concentration of Br2 at equilibrium is equal to 0.663 minus x, which would give us 0.663 minus 0.513. And that's going to give us an equilibrium concentration for that guy there of 0.150 molar. We could also do it for our product, which is Br. And at equilibrium, that is equal to 2x, as we can see there, right, in each of those. So that's equal to 2 times x. That would be 2 times 0.513 molar. That's going to give us, we'll call it 1.03 molar for our Br in this case. And those would give us now our equilibrium concentrations of what we are looking for. Any questions on that? Yeah. At the end, do I square the BR? We do not, because from the ice table, it actually equals 2x at the end at equilibrium. And that's where we took the 2 into account here. It's the stoichiometry. So it actually ends up, as you drive down there, to 2x in that case. Yeah. Yep. Other questions? Now, the good thing about math that everybody loves is it's math, which means I could check if I screwed up, right? So this wasn't a terribly hard quadratic, but I could check to see if I screwed up or not by doing what at this point. Yeah, now that I have the actual equilibrium concentrations, I could actually put those back into this, and it should equal a number like 7. Yeah, so if you take those concentrations that we just calculated for and put it back in there, you should hopefully get about 7. It may not be perfect with rounding, but it should definitely be in the 7 ballpark. I think you get 707 on this or something like that, so it's pretty good. If you put it back in and you got like 120, you definitely screwed up somewhere along the way. So it's a good idea if you have some time after you calculate those equilibrium concentrations, throw them back in there just to make sure, you didn't mess up somewhere. Again, this is not a super difficult quadratic one. There are some with a lot of numbers and a lot of factoring and stuff like that. So it's a good idea to just kind of check it at the end. Make sure you did all right. Any questions on that calculation there? All right. Well, I did one, so it seems like it's your turn now. So give it a go. A mixture of 0.5 moles of H2 and 0.5 moles of I2 are placed in a 1-liter flask. What is the equilibrium concentrations to everybody if the equilibrium constant is 54.3? Equation there on the bottom, H2 plus I2 gives you 2HI. Take a moment there, do your ice table, see what you come up with here. So here we got a mixture of H2, we got some I2 here. We're looking for some equilibrium concentrations, so we could do our K in this case is going to equal our HI concentration, and we're going to square it because of the coefficient, divided by our H2 concentration and our I2 concentration. And this is going to equal 54.3. Obviously, we need some concentrations. Once again, we have moles and liters, so this one not too bad. Our concentration of H2 going to be 0.5 moles per 1 liter. That gives us basically 0.5 molar. And same deal for our I2 in this case. That's going to get us here 0.5 moles over 1 liter, 0.5 molar in this case. Um, again, usually can't go wrong with an ice table if we're trying to find some type of equilibrium concentrations or pressures, and that's what we should do here. So I'm going to flip the page here and go this way, I think. And I'll steal this, I think. So initially here, I'll try to rewrite our equilibrium so we have it HI squared H2 I2 54.3. All right, so initially we have 0.5 here, we have 0.5 here. Once again, nothing mentioned about our products. Also here, obviously, we cannot calculate Q in this case, right? Because we don't have everything. Here we can go and assume that it is going to go in this direction since we have no products. So that's going to give us our minuses and our pluses in the correct sort of spot. This is going to be minus x, and plus 2x. Once again, we do want to make sure always to take into account the coefficients here. And carrying everybody down to the equilibrium line, 0.5 minus x, 0.5 minus x, and 2x. Any questions on the ice table here? Okay, so just like before, our goal here is really to solve for x. We're going to take our equilibrium line basically and pop everything into that expression. That's going to get us a 2x squared up on top, a 0.5 minus x, a 0.5 minus x. And that's going to equal 54.3. Obviously, in this case, we do want to solve for x, and hopefully you recognize that this is a perfect square on both sides. So just put like a big old square root on both sides would be a nice way to solve that. You could quadratic as well if you like. You could go that route. By the way, we'll give you the same answer whichever way. So if you just want to roll quadratic, you can. But in this case, you can perfect square it. It might save you some time. So that's going to give us 2x up on top. That's going to give us 0.5 minus x here. And the thing I personally always forget to do, actually take the square root there, 54.3 would be good as well. So that's going to get us a 7.3689. I might want to solve this more than the quadratic at this point here. So I'm going to multiply this to the other side. That's going to get me a 2x is equal to, looks like 3.6844 minus 7.3689x. Obviously, I'm going to bring my x's together, so I'm going to add this back to the other side. That's going to give me a 9.3689x equals 3.6844. Going to divide now, right? And now we're going to go 9.3689. Going to get us an x value here of 0.393 in this case. Questions on that there? All right, so that x is obviously all the x values that we see in our table, and now we could actually get our equilibrium concentrations. So the concentration of H2 is equal to 0.5 minus x at equilibrium, 0.5 minus 0.393 molar. Oops, 3. And that's going to get us 0.5 minus 0.393. Looks like a 0.107 molar. Don't forget the units as it is a concentration. Our I2 is going to come out exactly the same. So our I2 will also be 0.5 minus X, which is 0.393 molar. Going to get us the same number, hopefully, 107 molar. And lastly, here our HI is equal to 2x. So popping that in there, that's going to give us 2 times 0.393 molar. And that yields us a 0.786 molar as our concentration there for our products in this case. Any questions on that? Again, if you want to check yourself, you put those numbers back in to our expression, you get about 54. That's pretty good. Didn't screw up too bad there. So again, as I mentioned before, quadratic is a way that you could solve it. But there can be other ways, and this is like another way that you could. If you got a perfect square, avoid the quadratic. You don't necessarily do it, but you can still do it if you wanted to. And obviously, you should yield you the same answer. Any questions on any of that there? All right, now that our math is warmed up, let's do one that's a little bit more complicated and see how we end up. All right, same equation, same K value, but in this case, we're going to start with 0.00623 molar of H2, 0.00414 molar of I2, and we're going to have a little bit of 0.0224 molar of HI. We're looking for everybody's equilibrium concentrations. Give it a go. Probably not so much a perfect square on this one, I'm assuming. Okay, since we're getting to the end here, let's talk about this one here and see some things that we should think about. So obviously we're using the same equation and equilibrium constant as last time. We do have given to us H2, I2, and some information about HI. This is actually the second situation outside of a regular Q type problem that you should calculate Q in this case because you have all the information given to you and you should make sure you know which way this direction of this reaction is actually happening. So if we were going to calculate Q, it is done the same way as K as we saw before. We would take HI, we would square it, we would divide it by H2 and our I2. In this case, we would pop in our numbers, which is 0.0224 for our HI. Again, we're squaring it. We're dividing by our H2, which is 0.00623, and our 0.00414 for our I2. Putting all that into our handy dandy calculator here. See how I do here. My battery's on time. Let's see here. 0.00414. And that's going to give us a 19.5. Obviously, our equilibrium constant is right there. And that means in this particular case, our Q is less than our K. So it tells us we're not at equilibrium, which I could probably guess. Otherwise, it wouldn't be much of a problem at this point, right? Because you'd just be done if it wasn't equilibrium. But more importantly, it needs to go which way to reach equilibrium? It needs to go towards, does need to go towards the products, right? So we can now feel very confident when we do our ice table that when we get to our change part, we should have minuses on this side, right, and pluses on this side. Now, let's say, for example, I calculated Q and it was actually greater than K. What would happen in this case? Yeah, if it was the opposite, then really we're heading in, if Q was greater than K, we're heading in this direction, which means we would be decreasing these guys and we would be increasing these guys. So again, probably not going to come across it all that often. It's usually almost an automatic. It's going like left to right, but there are certain situations where you might want to check just to verify. And obviously you would hit in the opposite direction. By the way, you would do the ice table if it was doing in this direction the exact same way. It just obviously minuses on the right, plus on the left. The opposite thing that you could do as well if you had that situation is if you wanted to reverse the reaction, just to put your negatives on the left and your pluses on the right, you could. But if you reverse the reaction, you then would have to do what to the K? take 1 over the k value, which you could do as well. So, or you could just leave it like this and just have the pluses on the left and the minuses on the right if that was the situation. So there are a couple ways that you could kind of do that. Any questions on that there? All right. Well, it wasn't doing that, so I'll scratch it. All right. So we're going to do an ice table here. It's an ice table for sure. All right. So we got an H2. Leave myself some room here, I think. An I2 going this way and a little 2HI action. And obviously we could write our equilibrium expression here, which is the exact same one we did in the previous example. So we're going to go squared over H2 and I2, and that's going to equal our 54.3 in this case. All right, so initially here we got for our H2 0.00623. We got a 0.00414. And in this case, this is not 0. In this case, we got 0.0224 happening. Ice table here, we're going to go minus x, which we confirmed with our Q calculation that it is heading in that direction. We're going to do a plus 2x. And then obviously here, we're just going to bring everybody down. 0.00623 minus x, 0.00414 minus x, and this is 0.0224. Something people screw up on. They're so used to doing minuses at this point. This is plus here, right? 2x. Yeah. So not minus. Any questions on the ice table? This is going to go into our expression, and that is quite an expression, 0.0224 plus 2x. We're going to do a little squaring action. We're going to go 0.00623 minus x, 0.00414 minus x, and that's going to equal 54.3. This, unfortunately, is not a perfect square on both sides. This is a factor, FOIL, whatever you do with it these days. All right, so I'm going to kind of just split it off here and do top first and then do bottom, bring everybody back together just so we can see it here. So I'll go red for the top here. So I'm going to do top up on top here. So just the top part, which is essentially 0.0224 plus 2x twice, right? And you're going to go a little, when we do this, obviously a little in and out action. Sounds good. It is lunchtime, right? Going out action there. So if you do that, you will end up with 0.0005018 plus 0.0448x plus 0.0448x and a 4x squared. 4x squared there. Clean that mess up there. And plus 4x squared. Kind of combining everybody and turning the equation around, we end up with 4x squared up on top plus 0.0896x plus 0.000518. Now I'm going to do the bottom here. So I'll do the bottom in blue maybe. So we'll go blue for the bottom. All right, so on the bottom, we got 0.00623 minus x and 0.00414 minus x. Same deal, a little in and out there. So 0.0000258 minus 0.00623x minus, I'll go underneath since I ran out of room there, 0.00414x plus x squared. Again, kind of cleaning up my x's together. Going to get me an x squared minus 0.01037x plus 0.0000258 for my bottom. So this is technically what you should get on the bottom there when you factor it out. And obviously what I got on the red there is what you should get if you factored the top out. I'm now going to kind of put everybody back together and then kind of continue. I'm going to flip the page here, I think. And so up on top, we had, I'll go back to red, got to keep the same colors. What did I do there? Um, Up on top, we had 4x squared plus 0.0896x plus 0.000518 divided by on the bottom in blue x squared minus 0.010337x plus 0.000258. And that still is going to equal our 54.3 on the other side. I'm going to obviously multiply all that to the other side. That's going to leave the top untouched. And when we multiply that to the other side, that's going to give us 54.3x squared minus 0.5631x plus 0.001401. Obviously, we're at the point where we're going to combine terms. I'm going to take everybody on the left-hand side and just bring them on over to the right-hand side. That's going to give me 54.3 minus 4. That's going to get me a 50.3x squared. I'm then going to take this guy and subtract it to the other side, which will give me minus 0.6527x. Going to take this guy and subtract it to the other side. Going to get me a plus 0.000899 equals 0. That's going to be my A, B, and C here for my quadratic. Yeah. Going into my quadratic, minus B will give me 0.6527 plus or minus. If you do the square root, everybody inside, you get 0.24514. Upon the square rooting of it, 0.4951. That's going to be all divided by 2 times A, which is 50.3. Going to get you 100.6 on the bottom. Doing our positive first, I believe we'll get you an X value of 0.0114. Or if you do the subtraction, 0.00157. It's a long way to get those X values, huh? All right, so if we just look at our equilibrium line, obviously from our ice table, we got for our H2 0.00623 minus X, for our I2 0.00414 minus X, and for our HI, we have 0.0224 plus 2X. Looking at this number here looks a little too big because that's going to give me a negative number when I put it in there. So I'm going to go with that one as my winner. And that's going to get me 0.00623 minus 0.00157. And that's going to give me an H2 concentration of 0.00466 molar. I'm going to put my X value in for my I2, 0.00414 minus 0.00157. That's going to give me a equilibrium concentration for I2 of 0.00257 molar. And lastly, putting in my X value for there will give me 0.0224 plus 2 times 0.00157. Going to yield me a 0.0255 molar as my equilibrium concentration of HI. If you put those back in, you should get about 54, which I think you do. I did actually do it on the paper, just like you, just to see if I remember how. I don't know. So a little bit more complicated, hence the idea like you might want to throw it back in at the end just to make sure. Let's all leave on that happy note, shall we? All right.